Well, good afternoon, everybody. Wow, that quieted down quickly. But I noticed some not so familiar faces in the audience, so I just want to I'll introduce myself, Greg Deerline. I'm the director of the John A. Bloom Earthquake Engineering Center. And so this is the Bloom Distinguished Lecture we hold. This is the 24th one that we held. The first one was back in 2000. So one of the things we do before introducing today's speaker is just to talk a little bit about John Bloom, a little bit of his career, and the things he's contributed, because I think like many folks in industry, engineering, and academia, you know, things we do today, we inherited a lot of those ideas and knowledge from the people who came before us. So to just take a little kind of stock of that. John Bloom was a native Californian. He was born in 1909, just a few years after the 1906 earthquake. So he kind of grew up, you know, hearing about the earthquake and things like that. Actually, in 1925, the Santa Barbara earthquake was one that when he was kind of just getting ready for college, you know, so that was something that influenced him. So when he started here at 1929, he was very interested in earthquake engineering. And of course, from 1906 to 1929, here at Stanford and also some other universities in California, earthquake engineering got a big push. And if you visit the Bloom Center, you'll notice this model of the Alexander Building, kind of an analog computer of the time. And that was a topic that John Bloom worked on with a faculty member in mechanical engineering, Lydic Jacobson. And I think Lydic Jacobson had a number of students, John Bloom one of the key ones, that really worked on taking rigorous structural dynamics and bringing that into earthquake engineering and really into civil engineering, because I think at that time probably the advancements in dynamics and mechanics were kind of coming from mechanical into civil engineering. And John subsequently graduated and went on to have to create John Bloom and Associates, which was really a world-class engineering firm. Became very well known, and also over that time, John Bloom working with his contemporaries, people like Henry Degenkolb, other engineers from the 20th century that really worked together to take, you know, the knowledge coming out of universities, the observations of earthquakes, bringing that into the structural and earthquake engineering profession, and John brought that kind of through his firm. He returned to do a PhD, and he was by this time a very prominent engineer. People like Jim Geer, who were on the faculty, talked with trepidation to have John Bloom in their classroom at that time. Peter, you weren't here teaching yet, right? So, but you know, it was interesting. I've given this slide several times, 24 times, and I've often talked about John Bloom's engineer thesis, and I was thinking today, what was his PhD thesis on? So I looked it up actually, and it was on dynamic response of buildings, which is sort of what his engineer thesis was. The thing is, it was on computational modeling of that. And an interesting thing there's a few friends here from across the bay at Berkeley. One of John's acknowledgments in his thesis was an appreciation to Ray Clough and a young Ed Wilson, who shared some of their computer code with John to conduct the structural analyses he did. Kind of a remarkable bit of history there. And John was, of course, a great believer in lifelong learning. Coming back for the PhD was part of that. And his whole career kind of manifests that. This is a picture of the early shake table that was put in shortly after the 1906 earthquake, looking at structural models. There were also some studies of looking at ground deformations at the time. And in fact, a lot of John Bloom's, I was looking at some of his paper titles today, looking at introducing soil effects, thinking about the effects that had on ground motions. This was in the 1950s, these papers. And then John Bloom Associates, really kind of from those very early days, from that kind of analog shake table, bringing it forward into his company. This is just a snapshot of some of the projects that John Bloom and Associates worked on, in particular bringing in work here from Stanford with, that goes back to Jack Benjamin, Alan Cornell, and Haresh Shah in early seismic hazard analysis, and Karamidjian, looking at things like Diablo Canyon, Stanford Linear Accelerator, anywhere where there was kind of interesting or challenging aspects related to probabilistic seismic hazard, and also interesting mechanics problems like the NASA Ames wind tunnel and so forth. So kind of an amazing career. And John gave back one more way in that he endowed the Earthquake Engineering Center here in 1976. This is a picture of the two, John Bloom along with the two founding directors, Jim Geer and Haresh Shah at that time. And so John's always been really a leader in professional practice, research, and education. And of course, that's something we like to continue here in the Bloom Center, not just our research, but kind of bring that into practice and education. So this is just an occasion to kind of take note of that, especially for the younger folks in the audience who haven't been here over the years. My colleagues have maybe heard this presentation from me a few times, but something to remember. Okay, so next I'd like to introduce my colleague up, Christian Linder, who's going to introduce today's distinguished speaker. Thank you.
Thank you, Greg. Thank you, everybody, for coming. Thank you for our colleagues from Berkeley to driving all the way down here. It's a great event, great day today. Thank you to all the students who are here and participating in today's Bloom lecture. It's my great pleasure to introduce our this year's speaker, Professor Ekkehard Ramm. We are proud to have you here. Really happy that you made a long trip from Stuttgart here. He is currently an emeritus professor in the Department of Civil and Environmental Engineering at the University of Stuttgart in Germany. A little bit about his career after postdocs in Berkeley in the early 70s, and then also in Stuttgart he finished his habilitation and became an associate professor in 1976. He was promoted to full professor in 1983 and was head of the Institute of Structural Mechanics until his retirement in 2006. And shortly before he retired, I was also there in Stuttgart, and I was taking lectures from Ekkehard, and that was just an amazing experience for me back as a master's student at that time. Professor Ramm's research covers the full spectrum of structural mechanics and its numerical implementation into different discretization techniques, mostly into the finite element method. His work has an emphasis on thin-walled structures, in particular shells, and we'll hear more about shells tomorrow in his lecture in the afternoon, where Professor Ramm will give another lecture in addition to the Bloom lecture today. So shells are a big theme in his work. Just to show you how influential Professor Ramm was in the community of computational mechanics, I want to point out that 23 of his 57 PhD students went on to become successful professors at Stanford, in the US, in England, in Brazil, in Japan, in Canada. It's just an amazing community Professor Ramm was able to build with his students. He is the past president of GATSM, which is the German Association for Computational Mechanics, and also of the European Community on Computational Methods in Applied Sciences, ECOMAS. He was also the founder and partner in a successful consulting office in Stuttgart. He is an elected member of several academies, such as the German National Academy of Science and Engineering, and also the US National Academy of Engineering. He also received several awards, including 2 honorary doctorate degrees, one from the Technical University of Munich and one from the University of Calgary. He won the Gauss-Newton Medal of the IACM, which is the International Association for Computational Mechanics, and the Euler Medal of ECOMAS. These are the highest awards these organizations give out. His love for the topic he'll be talking today about the beautiful bridges in the Bay Area, they must have originated probably from the time when he first came to the Bay Area during his postdoc in the early 70s. And over the years, Ekkehard has collected many beautiful pictures of the bridges we have here and gained invaluable knowledge about the challenges these bridges faced during construction and afterwards until today. We're super excited to have you here, Ekkehard, to learn more about these wonderful bridges, the Golden Gate Bridge and the San Francisco-Oakland Bay Bridge. So, Ekkehard, the floor is yours.
Good afternoon, ladies and gentlemen. I'm glad that so many people came in particular, of course, also my friends from Berkeley. I appreciate that very much. Thank you very much, Greg and Christian, for this introduction. I'm glad to be here in Stanford again, and I'm very much honored to be selected for this Blume lecture this year. Talking about this unusual topic, given by somebody from another continent, looks a bit strange, you know. It is like what the English would say, bringing coal to Newcastle. So let's see how much coal it is. So I would like to start with my lecture, telling you a little bit how that happened, that something of this strange situation comes up. You know, it happened when I was here on sabbatical in 1989, and I went back to my own university, and we decided to establish a lecture series on the history of structural engineering. And we were looking for people who were giving these talks, and we didn't find enough. And then we said, we have to do it ourselves. And I said, okay, I will do that on the Golden Gate Bridge. I approached Alex Cordelis. He gave me a lot of material. And at the final end of this story here, at the beginning, there is this visit to the site. He invited me to the site, and we were able to, not to climb, but to go on top of the South Tower. It was an experience for me. So I would like to start now with my talk. You have heard Golden Gate Bridge and San Francisco-Oakland Bay Bridge from the beginning until today. And I would just start with the question, if you go to the internet and you ask about California in the early days, and there is this strange notion you find all over. It says California is an island. How comes? And of course, it's my imagination. It's not really said in the papers that it might be the Spaniards coming from the south. They saw the Gulf of California and the Baja California and thought we can extrapolate, you know, that goes further on, and that is an island. And you see on the left side a detail you find already in these days, the names, well-known names, Monterey and San Diego. And the first reference is given, and you know all probably here, Point Reyes National Seashore with Drake's Beach. And there is this Drake's Beach, very nice, located here. I indicated as 1579, the English explorer came here, apparently the first time that somebody has seen this area. But the official date is a little bit later, and it is here. I'm sorry that I have this sign here. Maybe I should go back. Okay. The official date was 1769. When the Spanish expedition came from southern California to the north, they were looking for Monterey Bay. It was foggy, and they found the Bay Area. It started the first settlement, as you can see here, 1776, and they called it Yerba Buena. Yerba Buena, the good herb, the green mint, and so on. And they started, of course, also a mission, San Francisco de Assisi, and much later, 1847, it was renamed after this San Francisco to this town. It had only 450 inhabitants at that time. So in these days, James Marshall finds gold at the Sierra, and this was found in the mill of John Sutter. I better should say Johann Sutter. He was Swiss at the time still. And this was the first discovery of gold. And you all know the story about gold rush. A call for emigration started. 1 year later, San Francisco had already 35,000 inhabitants. And even 1 year later, Captain Freeman names the strait Golden Gate, in analogy to the Golden Horn in the area of Istanbul. We call that now Istanbul, of course, Constantinople at that time, Golden Gate. And that was then the time in the late 19th century that the first proposals were done. How can we, get these get these connections to the other sides, to the north, Marin County, and to the east, to Oakland. And here you see some pictures, and the first proposal for a dam and a pontoon bridge from Oakland to Yerba Buena, what we call now Yerba Buena Island, is proposed already in 51. Regular ferry across the bay, and this famous story about the speculator and charlatan Emperor Norton I decrees to build a suspension bridge. Of course, it was nonsense. And then people proposed on the other side to continue the transcontinental Central Pacific Railroad, which reaches the bay. It would be very difficult. Later on, it had been done, a railroad connection, of course, in the South Bay, as you all know. On the other side, to the Marin County, the entrepreneur Charles Crocker proposes a railroad bridge across the Golden Gate. And then it happened. Earthquake 1906, magnitude 7.9. San Francisco was a metropolitan at that time, and it had already 400,000 inhabitants in this time. People moved because San Francisco was destroyed. Many people were passed away mainly by fire. People moved to the East Bay and to the Marin County. And then heavy traffic, ferry traffic started. A little bit later, 1930, it is reported that 50 million passengers passed from San Francisco to the East Bay. So now I come to the main part of my talk. I want to talk first about the San Francisco-Oakland Bay Bridge, the Bay Bridge, which is called here. You see here a modern picture, so to speak, a more modern picture. You see Treasure Island. It was not existing at that time. It was built 1939 for an international expedition. And in these days, 1931, the island was named Yerba Buena. It had different names before. From then on, it was called Yerba Buena. So talking about this official project of the state of California. It is a state of California which is standing behind us. There were already in the First World War hearings of the armed forces. They created later on in the 20s during the Depression the California Toll Bridge Authority. The federal government was also a little bit involved before the Congress, but they have withdrawn from this project, so the state had to take over. They made soil exploration first designed by this man called Purcell, Charles Henry Purcell. He started in Stanford with 1 or 2 semesters training, then went to Nebraska, and he became a state engineer in Oregon and in California then, and he was then selected as highway engineer for the Bay Bridge in 1930, and later on the chief highway engineer. The other one I'm showing here is Glenn Woodruff. He was the main design engineer, a very important person for this project. He was, by the way, later appointed to the board of engineers investigating the Tacoma failure of the Tacoma Bridge. And the final blueprints, and for me it is very amazing that this time from the starting point here, let's say 1930, until they began to build the structure, is a very short time. In comparison to the Golden Gate Bridges, was a much longer time, and they proposed all things and they planned something, but here it was very, very fast. So I cite here Woodruff, the main engineer. When the Bay Bridge was finished, he has written a report and he mentioned 4 points which are extraordinary projects. He said, we built the largest and deepest foundation on record, the world's largest tunnel. On the other side, we built this double suspension bridge, hooked together. We all know that. Each span 704 meters. And we built the largest and heaviest cantilever span in the US on the Oakland side. So that was later when he has written down that. And these people have done, of course, different studies. What kind of system can we use? We have not the time here to go into details. It's very interesting. There's one proposal here, one suspension bridge here. That was one very much like the Golden Gate Bridge here, almost the same span as you can see here. But others are proposed, and finally they have chosen these two suspension bridge. Ground anchored is an important factor. Ground anchored on the sides here, of course, and then here in the middle of this huge block. On the other side, you know what has been selected. Interesting enough, on both bridges, by the way, architects were involved in the outer appearance, in the aesthetics of the bridge. Here, it was the architect Timothy Pflüger, and he's seen here with the chief engineer Purcell. And he was the chairman of the Committee of Consulting Architects, and they have these wonderful architectural drawings. One is seen here. And here is a typical piece of work where architects influenced apparently also the final appearance. It says the comparison of a 1930 civil engineering sketch of the Bay Bridge suspension tower and a 1935 construction photo of the architectural committee design as built. Yeah, a little bit changed. They took out these horizontal bracings there. And Pflüger very likely designed the stepped semicircular tunnel entrance and exit portals, and by mounting a campaign of public pressure, preventing the bridge from being painted black, successfully substituting a silvery aluminum base instead. So the architects had apparently some influence. This is a discussion I had in all my academic life. The cooperation between architects and engineers, structural engineers. And it always coming up, and very often people find the names of very famous architects for bridges, but the engineers are not mentioned. So this was a very interesting construction going on. Of course, the foundation was a big challenge for them. Muddy soil on the San Francisco side, 73 meters below water level, and they used this kind of caisson technique, big boxes, you know, lowered, and here they had these airtight steel tubes, you know, to control the buoyancy, that they could lower the caisson down and could start the concreting and so on. This is a standard technology at that time. On the other side, you see this big block. They called it Moran's Island because the company was Moran's company, and he was the expert in deep water foundation. And they used more concrete than the Empire State Building was built. Then these towers in itself, fantastic buildings, prefabricated steel elements came from the East Coast via a railroad. And the company who built all the steel work was the American Bridge Company. And here I come back to Bloom, John Bloom. He, after graduating from Stanford University, Bloom worked as a construction engineer on the San Francisco-Oakland Bay Bridge in 1935 and 1936 until the bridge was opened. And there's this fantastic oral history series here, which one can look at, and I'm quoting here from that. At the time I started on the suspension side of the bridge, the towers had been erected and they were just starting the cable spinning. They assigned me as my first major stop to determine the correct final position for each of the strands in the main cables. I had to work at night to avoid the effects of sun and the steel, the temperature effects. And after the spinning was done, he was involved in measuring stress in the wire ropes and steel members. He used his expertise in dynamic theory. We heard about that, earthquake engineering and so on, but here he used it already for some other purposes. He said, by determining the frequency and knowing the approximate lengths of each rope, we were able to compute its tension. It went on the construction, that the so-called catwalk was established, seen here. The main cable were done, the spinning process started with all the individual wires pulled from one end to the other, and you see here these nice pictures. Then typical for ground-based suspension bridge, was anchored in the ground, that the construction is a very easy task because you can ship these elements, prefabricated elements, to site and you pull them simply up, and that's totally different from a self-anchored suspension bridge we see later on. So the double profile in the world, the largest profile in the world for the tunnel, seen here, I mentioned that. And then they started also the Oakland side bridge, this cantilever bridge, and they had this pier to the ferry there, and later on, of course, that disappeared. The truss type of cantilever bridging. And here you see it once more again. Opening of the bridge was 12th November 1936. And it cost over 77 million US dollars. And a sad story is 24 workmen lost their life on this site. So here, all these nice consulting people and essential people for the Bay Bridge are seen here, and I marked them a little bit in red. You can see they were also consultant for the Golden Gate Bridge, built in the same time parallel. They worked on both bridges, as you see here. We will see later on two names coming up, Moisaev and Modjeski. I will mention them later on also. And the blue ones are the people from the bridge, Purcell in the middle. And I also like to mention that Bloom was the 3-time winner of the IACE Leon Moisaev annual award, 3 times. It's amazing. So, and it's very interesting, maybe amazing or whatsoever, that the American Society of Civil Engineers, ASCE, has chosen the Bay Bridge in October 1955 as one of the American 7 modern civil engineering wonders. So they appreciated apparently these difficulties with these different situations, you know, and so on and so on. And it's interesting. But on the other hand, they changed their minds much later. In February '94, the American Society declared the Golden Gate Bridge one of the 7 wonders of the United States. Isn't that strange? It's of course both true, I would say. So then some people, Bob, you told me that you remember this, that there was this key system, a railway system on the bridge, and that was stopped in 1958 here, changing that to the second line, which we all know when we pass the bridge. Now, this Bay Bridge pictures taken by myself in 2007, always very nice pictures. And then we have to talk about seismic activities, of course. The faults coming in here in the play, San Andreas Fault, Highwood Fault, you all know that. The right picture shows the intensity of this earthquake from 1989, and you see the red parts and the white, the black parts here on that sketch. And all of you probably have seen these pictures one day, you know, on this main bridge on the Oakland side. This one deck, the upper deck, collapsed on the lower one, killed one person because this deck part slipped from the foundation there, coming down, as you all know. But the most severe damages on this type of bridge were on the approaching bridges on the Oakland side. Nobody really did, in my opinion. I don't know how you have handled that. When I went there later on, I was looking for what have they done for retrofitting on the San Francisco side. Nobody was talking about that, but you see it if you go there. These pictures I have taken myself. You see that, and I've read about that there are diagonal bracings on the decks, longitudinal bracing on the approaching viaducts. Look at the left part here in this case, how they strengthen the foundations here, that they do not uplift, and then real dampers. Okay, you can see wonderful, huge dampers established here on the bridge side. Then we have to talk about the new bridge on the Oakland side. And I'm a little bit afraid that you probably know more than I do, because you could follow the construction very much. I will only mention here that there were finally variants discussed, listed here by Caltrans, was responsible for that, and consulting companies. And in 1996, these were done, and you see here 1 tower, 2 towers, concrete, steel, and so on, and even nose tower on the right downside here, just extending the skyway. And they have chosen the self-anchored suspension bridge. Self-anchored suspension bridge. And that is a very different thing. And I remember, that's why I say you know more than I do, that there was a big discussion, not only in public, but also among the experts. Is that a correct structure, against earthquake attacks and so on? But they finally built it, and we hope it is right. At that moment, T.Y. Lin was involved heavily, and I show here typical leading engineers who have heavily involved in the bridge. Marvin Nader, he was already also involved in the retrofitting for the Golden Gate Bridge for T.Y. Lin. Then the Caltrans chief bridge engineer, Brian Maroney, and Frieda Seipler as a consultant professor in San Diego. And he did a lot of experimental work. Marvin Nader and Brian Maroney have written very nice journal papers. Here's one in the UK, recently published, and it is worthwhile to read them. So you all know about this new bridge, so I can be relatively short, I guess, in this sense. They called it a signature bridge because they want to have a signature in the landscape. Not only the Golden Gate Bridge is there. Here is also a bridge which is important. And here you see one tower, one steel tower, or here in the bottom you see the concrete part, of course, and the steel part here. Here's a walkway added here to the structure. And here you see this one tower with the cables coming down, self-anchored. I come back to that point in a minute. And so a little bit, maybe more for the experts, but I mention it anyway, design concepts. It's like in many of these countries, you know more about that than I do, because I'm not living in an earthquake-affected country, but we have worked in other countries where earthquake is playing an important role. Of course, we all know about energy dissipation, and you want to control that through local replaceable elements, the so-called fuses, mechanical fuses. And you would like to have movements available, independent movements of major structural components. No connection of the bridge and the tower can be seen here. The self-anchorage is a kind of independence of the local ground. It's important. And they say about the analysis they have done, time history analysis with global models, of course, under a large variety of earthquake scenarios, where they had these two different performance criteria. That's something for the experts. You know, the functional part of it, evaluation, earthquake with immediately full service after the earthquake happens and minimal damage. And on the other side, you would not like to have a failure of the bridge, safety evaluation, earthquake, that it could be repairable, of course, and so on. And that has been done here. The skyway, the concrete done, is essentially a traditional type of construction. You know, it is the precast elements here. You see that the elements here pulled up here and hooked to the existing part. And here the specialty is, of course, that you have those two lanes. You all know that. The environmentalist had an influence, as you can see. They added albatross nests here. They had to do that. That's what I read. And then another fuse here between the concrete part, the skyway part, and the steel part, you know, the so-called hinge pipe beams. And this fuse is added, and here you see a middle part of it, orange part, which is thinner and has lower grade steel and is supposed to be plastify, you know, to take the energy. That is the idea. And then you can take out the entire pipe here, put a new one in, and that's it. That was the idea. So then also a very interesting phase of the Bay Bridge started, of the new Bay Bridge started. They had all these bids coming in for the steelwork of the bridge. And of course, United States companies, Japan, Japanese, Chinese, all over the world, French, and so on, Japanese and Chinese, of course, and they did win the story, as you know, the Chinese company. And then this company here, Shanghai Tsinghua Heavy Industry, has never built a bridge before. They were famous for cranes and sold cranes all over the world. Even in the United States, most of the cranes are used from that company. And they did win, and it was probably not so easy for the American people to stand this situation. So here you see how they shipped this start here from Shanghai. They built a huge factory in Shanghai. I've seen pictures of how they did weld all these elements. And on the right side here you see what now is a difference to the ground-anchored construction. Now you need these temporary truss false work because the cable is not able to carry this stuff, you know, because it's not yet really fastened in the girder. The girder is not existing. So Shanghai Tsinghua Heavy Industry here, once more again, a right picture, the catwalk and so on. And here another energy dissipation element here in the tower. There are 4 legs, as you can see. You see them under construction here. And you see this place is still open, and there should be shearlings added, and they are supposed to plastify, to take the energy in the structure, and could, of course, be, in case of an earthquake, replaced later on without damaging the entire structure. That was the idea. And also, these shearlings have been intensively investigated. You see here such an element, and it has been tested full scale. It is UCSD at the Jacobs School, and you see this man here standing here. That was a huge operation, as you might recognize. The main cable also produced in China, and the different from the Golden Gate Bridge, which we see later on, and from the old San Francisco side here, not the individual wires come to the side and are carried over by spinning process. Here is the entire strand has been wound up here. You see this element here, and then put here to the main cable. Self-anchorage, once more again. So we see here how it works. You know, you can see that the forces come here down, you know, and then they go down again, here up, and go down, so and so on, and go underneath here at the final end. And this is shortcut system. It's a self-anchored suspension bridge. On the right side, you see this anchored type on top of the bridge here. And the horizontal cable conduit at the end here, at this part, is shown here. So opening September 2013, you might all remember that situation, $6.5 billion cost. And here you see the wonderful picture of both bridges, the same here, the bicycle lane coming up. And that is a big disadvantage for the people because the bicycle lane stops on the island and you cannot go to San Francisco. So then the old part had to be demolished, you know, 2018 finished, as you can see, and they did it just the same way as they built it, just the other way around, reverse. In particular, you have seen these pictures here before, you know, as if you would build them though together. Now they took them apart, yeah, and here taking off and lowering this system by strand jack system, yeah. So I had the opportunity, my students did give me that as gift, to fly, have a scenic flight with a seaplane with my wife together in 2007, and I have taken these pictures here from the two bridges. Wonderful. So I come now to the next bridge, San Francisco Golden Gate Bridge. Okay. There's so many nice pictures. I don't have to show too many of them. But I will tell you how that started. In the World War I, 1916, the civil engineer and editor James Wilkins proposes in the San Francisco Bulletin a bridge across the Golden Gate. And a little bit later, the San Francisco city engineer O'Shaughnessy begins inquiry among major bridge engineers in the US. All answers, except one, are negative. Too risky and too expensive. It would cost $100 million. Impossible. This one man was Joseph Beermann Strauss, at that time 48 years old. Now I have to tell you a little bit about the story, what I read, of course, and you know the person born in Cincinnati of extreme short stature, talented in math and mechanics, interesting, graduated in 1892 with a thesis to span the Bering Strait, extremely ambitious and had an enormous ego, not an easy character, it is said, a rather tough person. His intention was to make everything better and larger than others. But he had a lot of visions. Good sign, I would say. And Strauss did work in Chicago with Rod Modjeski. We have seen him in the picture for the Bay Bridge already. After a dispute with Modjeski on a basketball bridge, he left the office, started his own business. On this business, or this consulting office, designed 399 bridges, smaller ones, of course, in the US and other countries. And Strauss said, I can do it, and for far much less. That was his statement. He did believe in that, and he was right. And then he came up a year later with this, you could call it fantastic bridge. It's such an ugly structure that there was opposition apparently from all sides. You know, we will not have that bridge. And fortunately, this has not been built. This is a really, and also his second design is not much better. So, but now in 1925, another person involved in this, we have heard that name, Moissaieff, also already, came into play, and he proposed a real suspension bridge, which we all know. It happened like that. He proposed that. It's not Strauss did that, He was the expert for this kind of structures in that time. Here you see a painting from Meinhard Dixon, done for the bond issue presentation in 1930, another painting on the other side. And I have to tell you now again of this famous engineer Moissaieff on the one side, here, played an important role, suspension and expert, and on the other side of somebody in Joseph Berman Strauss's office called Charles Ellis. And this story between the both, I would like to quote a little bit of this report, American Experience, and so on, because it's essential for the situation which comes up now. Moissaieff worked in tandem with Charles Ellis on the engineering of the Golden Gate Bridge. Moissaieff especially contributed to the force calculations related to wind impact on the bridge. From his New York office, he traded telegrams with Ellis in Chicago, going over an endless string of engineering questions. And then it is said, together, Moissaieff and Ellis explored the practical application of Moissaieff's deflection theory of suspension bridges. They made their bridge design flexible enough to withstand the gales that often blew through the Golden Gate. And I would like to add, the suspension bridge theory is based on a theory of the Austrian academician Joseph Melan from 1888, and Moissaieff adapted that and refined that a little bit and so on. This picture shows also some famous people, as you can see here. But there in the late 20s, there was this proposal from Moissaieff, suspension bridge. There were a lot of problems coming up that they had to solve. The foundation, in particular for the South Tower, it's in the water, as you know, and they were not sure what kind of soil they could expect. It was really muddy and not very good soil. They made test drillings and so on. Finally, they found it can be done. The armed forces harbor there, in Oakland Harbor, they have this military base. They were very strong, very much against this bridge at the first beginning, because they were afraid when something happens with the bridge, we cannot use the harbor anymore, or the base anymore. And then there was this enormous pressure from the people. You have to do something now. The ferry traffic was immense at the time. And then we have to talk about finances. And it is not it is a public bridge, of course, but on the other side, it is not the state of California, not the federal state. It is a district. The district means San Francisco and I guess 5 counties of the north, Marin County, for example, they make the district, and they are responsible. And they are not rich enough to support to build such a bridge. They needed external money, bonds. And in this phase, Strauss played the decisive role in the implementation of the project. And it was a time of the Great Depression. He used the argument, the bridge against unemployment. In December 28, courts decided the bridge can be built. A little bit later, not by mere chance, that Strauss did win the competition for the post of chief engineer, and he was clever enough to choose his competitors as consultants. So they were also involved. They were not opposing his project. End of 1930, the people had to decide that the bridge can be built. And the proposition, it was 3-1 in favor of the bridge as a project. And now I come back to Ellis, the man who cooperated with Moiseiff. I mentioned that. And he was hired by Strauss in 1921 already in his Chicago office. He was working all the time, most of the time, until 1931. And then, on a sudden, was fired by Strauss. And he went to Purdue, became a professor, a well-known professor. And it is, in a way, a sad story, because he was not mentioned at all by Strauss. In the final report he has given in 1936, the other man, it was an assistant of Ellis, Clifford Payne, was appointed principal assistant engineer, and he is listed in the report, and he is listed when you go there to the Golden Gate Bridge. You see on the South Tower there is a plug there. Then you see the name Clifford Payne, but not Ellis. And this story has been taken up by a journalist, so to speak, a writer, John van der Zee. He was the author of a dozen books, and he has a contact with the son of Cohn. I will tell you where Cohn was just in a minute. And he wrote a book, a bestseller, this book here, bestseller, The Gate. The true story about the gate. And it took a long time that the work was acknowledged, and he has talked to the father of the son I mentioned was Russell Cohn. And Russell Cohn was the supervising engineer on site during the construction of the bridge. And he had all the original engineering documents from Ellis with Ellis' signature. So that was the document that he needed. And he has published this book, became a famous story. And in the meantime, 75 years later, AECE acknowledged that work of Ellis and added here in 2012 this plaque to the Golden Gate Bridge. So I have to talk a little bit about the blueprints here. You know, at that time they were really blue blueprints. You have to know that on the left side, you know, there is this soft soil, you know, serpentine here. That is important. Here's this arch, you know, on the north side. It's a very stiff, sound material, diabase basalt, very strong, you know, very easy to make a foundation. And I added this here because it's my opinion it is very interesting. The dead load of these main structure, except the cable and so on. For the cables, the dead load means 31%, truss girder 16%, 18% for the steel deck, and the concrete deck, 30% for the concrete deck here. And the dead load here, if we have 100%, then the life load is only 19% of this. Very typical for these huge bridges, of course, you know. You have to have enough material to carry a little bit of load, so to speak. And Moiseiff said the effect of earthquake was found to be considerably less than that of a strong wind, and he was completely wrong. We know that nowadays. So an architect came into play here also, or I would say, better say, two architects, Gertrude and Irving Morrow, architects, and they had an important influence on the outer aesthetics of the bridge. And as you know, he defined the color. I come back to that later. And here you see the situation, what the Morrows did, you know, in particular the towers. Here they had the cladding of the diagonal bracings here and so on. They made, and then these, you know, stepping down with the thickness of these columns here on the side and the decreasing ascent. That is Morrow's proposal, and I think it's very nice. And all these Art Deco decoration of the bridge here, you know, light posts and pedestrian railings and so on, are based on the proposals of the Morrows. The start of construction, 1933, Mayor Rossi came here. Then the foundation of the North Tower, very simple, very classical here. They could make a cofferdam, as it's called, and make a dry construction site and could just concrete as a usual tower would be built. And then the abutments, these huge blocks. We have this situation that the cable forces has to be anchored in ground. The boxes had to be very big, the abutments. You see that in the north, very simple here, but huge. And here in the south, a bit more difficult because of the soft soil. And then you see here the Fort Point. They had to add the Fort Point construction to that, and the forces from the arch had to be taken. So the most difficult part in the construction time of the Golden Gate Arch was this situation here. The foundation of the South Tower here, you see the fort here, they built a trestle bridge here, and they started here the so-called fender, a steel construction lowered down to the ground here. And then again, a caisson should be placed there, that they shipped the caisson here. And then it started, at that very moment, started a strong storm that tossed and pitched so badly that they almost destroyed the fender when they came here in that situation. And they took it out and they scuttled it in the bay. I don't know where, but anywhere there must be someplace. So then it happened. 1933, this Threttle Bridge collapsed due to freighter crash. Shortly thereafter, a heavy storm came, another collapse, another destroyment. It was really a big challenge for them, and they really didn't know what kind of construction do we have, and they changed the caisson construction into conventional foundations. They had these fender here, this situation on steel structure, and now they could really start underwater concreting and so on. And then they had these little inspection shells here coming in that they could really see what kind of soil they could have here. And is it true what we have investigated? That was apparently a big question. I like this picture very much. It's a picture from the Smithsonian American Art Museum. It shows this situation from the south, Fort Point here, just in the middle of this construction. And the tower is a little bit seen here. And President Franklin Roosevelt has chosen this painting celebrating the triumph of American engineering to hang in the White House. And as a structural engineer, structural analysis man, I was interested, what have they written in the books? Strauss, in his final book about analysis, very little. He didn't mention at all Moises' influence. He didn't mention at all Ellis' influence, nothing. The only thing was some words about the analysis you see here sometimes. Maybe I should ask the question, who knows what a Villieu plan is? Bob Taylor knows it. Oh, you too. Okay. I will not explain that. This is not so important. We got to have another story. And then here, of course, the moments. And I found this sentence in the report of Strauss. The analysis of the towers was finally concluded with a set of 33 simultaneous equations. A lot. Since most of these equations did not contain more than half a dozen unknowns, the solution was not difficult. Okay, they were not sure about their analysis, and they made model tests. You have heard about that probably, that in Princeton they made these model tests, very nice models. I've seen them when I visited Sarah, your father, and Maria Garlock, and at that moment I had made these pictures, very nice pictures of these models and prints them. These drawings here, they are art pieces in my opinion. Every rivet is shown there, and really very nice work. And you see on this side, how big these towers are. Empire State Building, a little bit earlier built, a little bit higher, of course, and then the other towers lit on. And here, the anchor block and on the top, and all these elements with all the rivets and so on, shown. And important, we have a U-type of girder. A U-type of girder. Here, the main frames here, and then the beams in between. And once more again, it's a riveted construction. All the rivets had to be placed, and that was a heavy work at the time. So, and these elements also came from the east, Bethlehem Steel in Pennsylvania, and they were shipped through the Panama Canal. The North Tower was built, the South Tower. At that point time, they were very flexible. There's no cable existing. Could fix that a little bit. It was very flexible, apparently. And then it happened that the painters and riveters, had these lead poisoning. They suffered from teeth and hair loss and shortness of breath and with dizziness and nausea. And so on, they got some respirators and vitamin-rich food. It was a serious problem. It was hard work. They had to rivet inside these boxes, and these rivets were heated up. They were hot and shot there into these boxes and had to be placed in their correct position. The cable block, the Röblings came. The Röblings came from New York, and the Röblings, it said they were tough people, very strong. They hired and fired. I heard about that. They want to be ready in 6 months, and they did it. The cable saddle, huge metal block here, pulled up here at that time in all the places. Then the catwalk again. And the spinning process began again. This is, by the way, going back to Louis Vicard, a Frenchman, cable spinning method, 1829. So it's a conventional method, but applied in a huge structure, of course. So here's some shots from this situation. There's the funicular pulling these little wires from one side to the other. The cable had to be the strands, and then they are compacted together. Underneath this figure, this photo, I saw the name, the first commuter. It's a nice man with an ordinary hat, walking on the catwalk. And so on, and then they started the girder construction. The girder construction, prefabricated in Pennsylvania, I mentioned that, and you see here one piece in this picture, that is this one here, and there are people inside this net, and Strauss was concerned about safety. It was Strauss' idea to add this safety net. It was never done before, and this is the first time that they did it. And it saved a lot of lives. And these people, founded the Fellow of the Bridge Club or the Halfway to Hell Club. So they were slightly behind the Bay Bridge. The Bay Bridge was already opened here in October 1936. And this is an amazing picture. I read that the people were afraid that they will never make it here to find the connection between both, but they have investigated the situation carefully by experimental type of work and so on, tested that, and we have seen that worked out. And here you see the rest of the structure, and the bridge was already fixed. And then Morrow comes, of course, again the color comes into play here, and the international orange. Why international orange? He played around with some test paintings, black, silver, the military ships, silver, of course, and so on. But we finally insisted on this color. And when I was in '89 in Berkeley, I read in a newspaper that somebody said we have to change this color, it's too expensive and so on. And there was an uprising, we want to have the orange still existing here, and that will be never changed. And then, unfortunately, this happened. In almost finished situation, a scaffolding part fall down into the net and pulled 10 people, more than 10 people. Some could be rescued, I guess, but they had 10 fatalities, and one person was killed when a derrick on top of the bridge failed and killed another man. 11. We had 24 in the Bay Bridge. So, opening in May 1933, Strauss again, Rossi came, cut the chain here, and so on. And here there's a saying that was a golden rivet, a golden rivet. They could not set that rivet at that moment, and they put it in another place in the bridge, and nobody knows where that is. So opening with a pedestrian day, an automobile day, and all the people had to pay, by the way. I would say typical American. So, okay. Now we come to the end of Strauss's part here, and he quoted O'Shaughnessy, everybody says it can't be done, and even if it could be done, it would cost over $100 million. And I said, I believe I can do it, and for far less. And then 20 years later, he said, it took 2 decades and 200 million words to convince people that the bridge was feasible, but only 4 years and $35 million to build it. So, and Strauss left the part and went to Southern California and passed away 1 year later by a thrombosis. So he has written this report. I said I mentioned that there's only Clifford Payne mentioned, but not Ellis, and Moissaif is only mentioned as consulting, although he had an essential impact on that situation. So you can make thousands of pictures of this nice bridge and so on, and then it happened. You all, I'm sure, have seen this movie. Is there somebody who has not seen the movie? The Tacoma Bridge failure in 1940. So here you can see how flexible suspension bridges are before they collapse. And I found it amazing what they really does, and movement. Before it's destroyed. Torsional thing there's this cut. Pardon? Is this real cut? I think so. And there's one dog, unfortunately, in this car. He was killed. So now it failed. Okay. And the tragedy was that it was Leon Moissaif's design. So there was a tragedy for the man, who was responsible for that bridge. Oh, no, not Iran. We have done, of course, for our students and so on, we've done these kind of modeling, and you see here the Tacoma narrow bridge situation where these pressure balls, from one side to the other, and have these torsional movements here, and this streamline cross-section does nothing here. Okay, so that is a failure. The Golden Gate Bridge had this U part here. The Tacoma Bridge, very slender, almost no torsional stiffness. But also here, a U shape has very little torsional stiffness. And as George Washington, they added later on a lower deck here. It is a box, much better, of course. And there are many bridges in the world, of course, where they have chosen these streamlined cross sections, you know, to avoid these wind effects and so on. And they were very much concerned on the Golden Gate Bridge. What should we do now? It survived already heavy winds until 1940, but they said we want to be on the safe side, and they added a lower bracing here. If you go there, you can see that. You might not recognize it in the moment, but it is now a U-type cross-section, and the torsional stiffness is increasing by the factor of 50. So next challenge, the climate. 1967-1969, there was a major inspection of the bridge by Ammann and Whitney, and they found in particular that the suspender ropes and connection were substantially corroded, some of all also already in critical state, and they are soon thereafter replaced. International orange, and they are painting continuously on the bridge. That is said in the report of the Golden Gate District. It is wet there, all the wind is coming and so on. And at home I have this gusset plate from the bridge. It's taken off, and I didn't steal it from the place. My student came one day who has visited the place and gave it to me. You are interested in the Golden Gate Bridge? And they gave me this piece of paper with their signatures. You see how corroded this stuff is, and so I have it at home. So then another challenge, the loads. What about the loads? They're replaced one day, not many days, many weeks. They replaced the reinforced concrete deck, 30% of the dead load, and replaced it by steel load. And you see now the S shape of the situation here at that moment. And the reduction of the dead load is now 17%, which is substantial. It's a lot. And here, on the 50th anniversary, 1987, the bridge was full of people. Some people, I've read that some people were afraid. Oh, can that stand that? Because they have seen this picture. It's almost flat. But it is no problem. You can analyze it a little bit, it's no problem. So in this time, I was a little bit earlier, I was in Berkeley again, and somebody sent me a year later this little article, Trains on the Golden Gate Bridge. They made a feasibility study because of this heavy traffic and ferry traffic and so on. Can we extend the BART system? And one of these trains here is BART. I don't know which one. The other one is a kind of tram situation. Here you see a kind of image of that potential, but that was too expensive. They didn't do it. Then the next challenge comes up, earthquake. Earthquake, I don't have to tell you something about earthquake. I only want to mention what happened to the Golden Gate Bridge. And this is from 2003, always shown also on the website of the Golden Gate Bridge, this picture of the probability of a magnitude of 6.7 or greater quakes before 2032. 2032. And if you count them together here, 62%. So the probability is there. We cannot change that. Already in the 1990s, I would say, T.Y. Lin made analyses of how should we replace certain elements and so on. Local models were done, experiments in Berkeley were done. Here's one scene on the right side. And since then, beginning at 1997, they started this retrofitting project, which is going on, and it will go on another, I would say 5 years, 6 years, where they started on the approaching viaducts, here shown in green, on the left side and the right side, south and north. left side is its arch we've seen, on the right side is the Marine County side, because these parts of the bridge were the most vulnerable parts, and they changed it at first. And the main part in the middle here will be done in this, we begin shortly in this retrofitting of the main part. And I don't have the time to go into details here, but it's substantial what they have done in the meantime. They replaced complete towers here. You know, I guess this one is completely restored, built new. Here the foundation of this arch is replaced, it is fixed and so on. A lot of EDDs have been added here, on dissipation elements, I should say. And in this very moment, I would like to mention Eva Zett-Bauer. Bob, you know her, you remember that she was our guide on the site when we were together there one day. He is a chief engineer officer of the Highway and Transportation District. And I would say, if I'm allowed to, she is probably one of the most successful female engineers of the US. And she got these outstanding for the project, the Outstanding Civil Engineering Achievement, the OCEA Award for the seismic retrofitting phase 2. She's a member of the National Academy of Construction and ACE Outstanding Projects and Leaders Award. So she is really very competent. And by the way, she's from Poland. She is trained, she is a master of engineering and from Poland, and went to the States and became this successful engineer. And here you see what goes on. This is an interesting picture. I see him in the next picture, in the next slide again. You see they look like the old bridge, you know, these elements, bolted. In the back you might see here bolted elements, but I think if we see it in the next one even much better. Here, no, we cannot see that. But you can, maybe in the next slide. Here's a new foundation for the arch. You know, it's renewed support, and you see bolted, heavily bolted elements in connections and so on. This one is completely renewed here, and maybe you see it a little bit here, that the new, you know, look like the old riveted bracing elements, but they are laser cut of an entire piece, you know. So base isolation coming in, you know, these rubber blocks here, seismic isolators, and so on and so on. A lot to be seen. You can see them when you go there. Here's a new tower there, extra reinforced concrete layer on the pier. Here, that is a picture I meant. You know, you see the old one, and that didn't want to change the outer appearance, you know, want to have the outer appearance, the aesthetics should not be changed, and that this is not, of course, a different situation. So, the bridge is used, I better say misused, as a marketing object. Left, you know, your wallet is here and you are here, and for American Express, and in the Frankfurt airport I saw this silly picture, and you find them all over for the bridge. And it is used for demonstrations. This one here, that came from University of British Columbia, from Vancouver in 2001. Because I had some connection to them, they sent me this picture here, where they dangled this VW bug body prank situation here, or then the free Tibet demonstration. Alain Robert, the free climber, the Spider-Man climbed up, and so on. And it was also misused. I come soon to an end. This one I found interesting to show it. Up to the, I don't know when they did it, 2015, when they changed from morning to the evening, they changed the lane, the number of lanes from one side to the other. They had this barrier in the middle, and then they had to close the traffic and place these elements there in between, and then they found this nice machine here, the road zipper truck, which does it in minutes, you know, from one side to the other. The Golden Gate Bridge 75th anniversary came up with a big celebration. I have not seen anything about the 85th anniversary. Do they have forgotten it or what? And then we have to talk about the sad side of the Golden Gate Bridge, the tragic side. The bridge has these lots of suicides. And the official count ended in 1995. Media were asked to stop reporting, not encouraging people to do that. And the Golden Gate website mentioned 30 people and more die each year from suicide. Hundreds more, fortunately, are stopped through highway and district patrol and the efforts of the citizen. And they have all these devices to prevent the people from jumping down. So, and in the meantime, the district board of directors, they made some feasibility studies. And at that time, I read that they were had not a unique meaning of that. They were split. The one said, yes, we have to do that. There were others in the board who said, no, let them do it. We don't interfere here. But they did it, fortunately, in my opinion. And they have, finally, here are some examples of the vertical parts. You know, the aesthetics is influenced, of course. The aerodynamic situation is influenced. They made wind tunnel tests and so on. And finally, they decided to choose this safety net. Here, a safety net. And this is a construction you find in cathedrals sometimes, also in towers, of course. And apparently, they hinder people from jumping down. Because I had at the very first beginning also to jump on the net and then go on. Apparently, it has some influence, fortunately, I would say. Well, then finally, they approved that, and it is built. And on January 6th this year, I read in the San Francisco Chronicle, the Golden Gate Bridge suicide nets are nearly finished. So they finished the project, and let's hope that it is working. So my views from the South Tower and from the North Tower, and I would like to say the Golden Gate Bridge was for many years, 27 years, the bridge with the largest span before the Verrazano Narrows Bridge came in. And in the meantime, there are many, many others, as you see here. The biggest one, the largest one, with a span of over 2 kilometers, 2,000 meters in Turkey, just recently, 2022. And there might not be the end. People are talking about the bridge of the Messina Strait, and it has 5 kilometers span. It is a project and has all the detailed engineering done already, but turned down from past governments in Italy. But the new one, this lady is governing there now, Meloni, she wants to have that bridge. So let's see. So then you all know when you go to the south end of the Golden Gate Bridge, there is this statue. And it is Josef Berman Strauss, 1815, 1938. And this has this plaque here, and it says, the man who built the bridge. The man who built the bridge. One man built the bridge. I mean, this is, of course, nonsense, but I mean, he had a tremendous influence in the implementation, and there were many others. Unfortunately, he has not recognized all of them. Ellis, for example. And with this slide, And that one, with thanks to my guides, I've been often on site here, also with Bob here, and Brian Maroney and Frida Seibler on the other side. And the thanks to my dear friends and colleagues, Alex Cordelis and Carl Piester, and for you, Bob Taylor, I'm so glad that you are here today. Thank you so much. Yeah. Thank you all very much for your attention.
Thank you very much, Ekkehard, for this wonderful journey back in town. We'll open the talk for a few questions, if there are any. There is a reception afterwards outside, so there will be time to mingle with our speaker, but maybe there are a few questions here. Any questions?
Let's do it outside.
Want to do it outside? Okay. Then let's thank our speaker, Ekkehard. That was an amazing... We'll have a reception outside. Thank you. Wunderbar.